Howdy, and welcome to the enhancement lecture on reversible, irreversible, and impossible processes. So I don't have that in the title here, but in fact we will be talking about impossible processes a little bit toward the end. So I just want to caution you ahead of time that this is a rather long video lecture, and so you might want to plan on watching it in parts. The other thing that I need to mention is that this video lecture is going to discuss some of the most important concepts that we want you to learn from thermodynamics. In fact, I would even argue to say that these are the most important concepts that you need to understand about thermodynamics as a good engineer. So you might want to consider watching it a few times since the concepts can be somewhat complicated. And watching it a few times and even after you graduate from the class may be beneficial for you. Okay, so we're going to talk about reversible, irreversible, and impossible processes. And to begin, it's very helpful to define what we mean when we say a reversible process. So to define, let's first start by centering our attention on a control system. And so I have here this basic control system. And just to simplify the discussion, it's not necessary, but just to simplify the discussion, we're going to assume that the system is closed, so there's no mass transfer. There's no reason that the system has to be closed. It could in fact be an open system with mass transfer in and mass transfer out. That just kind of adds a level of complexity that's not really necessary for us to understand the concepts. So we have this closed system, and it undergoes a process as it goes from its initial state, which we're going to call state 1, to its final state, which we're going to call state 2. And of course, in that process, the energy of the system can change from its state 1 energy to its state 2 energy, and the entropy of the system can change from its state 1 entropy to its state 2 entropy. Of course, the system is interacting with its surroundings, and that interaction can involve heat transfer, the transfer of thermal energy, and we're drawing it in the positive orientation so that thermal energy transfers from the surroundings to the system in the positive sense. And likewise, we can have a work transfer interaction where also drawn in the positive orientation, the work transfer is from the system to the surroundings. So the system is doing work on the surroundings basically. Okay, so if we say that this process, as the system goes from state 1 to state 2, is reversible, what that means is the following down here in this paragraph. If this process is reversible, it means the system and the surroundings can be returned to their original states with no net change done to either the system or the surroundings. So if I were to draw what this means in a picture, we have this forward process where we go from state 1 to state 2, and in that forward process, the system accepts thermal energy from the surroundings, Q1 to 2, and it transfers work energy from the system to the surroundings. That's the forward direction. So now imagine that our system is at state 2, and we want to return it back to its initial state. Well, if we want to return it back to its initial state and have the process be reversible, what that means is that we need to reverse the direction of work 1 to 2 so that we take the work from the surroundings and put it back into the system. That then would cause the system to need to reject thermal energy from itself into the surroundings. So we would reverse the direction of Q1 to 2 so that thermal energy transfer is from the system to the surroundings, and the energy and entropy of the system would return to their initial states, the initial values at state 1. In other words, the energy of the system at state 2 and the entropy of the system at state 2 would return back to their state 1 and state 1 energy and state 1 entropy if this whole process was reversible. And so that's what we have drawn here. In the case of a reversible process, we can reverse the direction of work transfer so that the work transfer is from the surroundings to the system. So this work 2 to 1 is in fact equal to the negative of work 1 to 2 from our earlier above drawing. Likewise, the system will transfer thermal energy from itself to the surroundings. And so we would have Q2 to 1, where Q2 to 1 is exactly equal to negative Q1 to 2. It's just the reverse direction of that thermal energy transfer from state 1 to state 2. And our system energy goes from the energy at state 2 back to the energy at state 1. And the entropy of the system goes from its entropy at state 2 back to its original entropy at state 1. And so what we've done here is we've returned the system and the surroundings to their initial states or their initial condition. And if after doing this with the forward and the reverse process, if the system and the surroundings are back to their original states with no net change done to either the system or the surroundings, then we can define that process as being reversible. So a reversible process is essentially what we would call an ideal process. It's basically the ideal process for a system interacting with its surroundings. Okay, so this is all somewhat abstract, right? The idea of a reversible process is a little bit, and the way that we're defining the reversible process here is a little bit abstract, and sometimes it's easier to think about what a reversible process is by thinking about what irreversible processes are. And you already get the sense that if the reversible process is the ideal process, then the irreversible process or irreversible processes, since there are many types of irreversible processes, as we'll talk about in just a minute, are the real cases. In other words, what we deal with in real life are irreversible processes. So, what are some irreversible processes, or what is an irreversible process? Well, the definition of an irreversible process is basically just a play on words from the definition of a reversible process. The way we define an irreversible process is one which causes a net change to either the system or the surroundings or both. And typically in an irreversible process, it is the surroundings that is irreversibly changed. In other words, we can almost always return a system to its initial state. We can almost always get a system back to its state 1 condition. But we may have to irreversibly alter the surroundings in order to get our system back to its initial state. Okay, so again, that's the definition of an irreversible process, but sometimes it's much easier to think about an irreversible process by giving examples of irreversible processes. So, a very common or conventional example of an irreversible process is to think about the cooling of say a hot cup of coffee, or a hot tea or hot chocolate, whatever your beverage of choice is, just so long as that it's at a higher temperature than the surroundings. So we have our system here. So our system is this really awesome Texas A&M coffee cup. And in fact, that is actually what my coffee cup looks like at home. So I just drew that for y'all. And this hot cup of coffee is at an initial state where perhaps the temperature of the system, that is the temperature of the coffee, is about 120 degrees Fahrenheit, okay? And that hot cup of coffee is sitting in the surroundings, which might be at about 75 degrees Fahrenheit. So of course, if I pour my cup of coffee in the morning, the coffee is hot, the surroundings are relatively cooler, there is going to be a heat transfer from my system, my cup of coffee, into the surroundings. That's why I drew my arrow from the system to the surroundings to indicate that the cup of coffee is going to transfer thermal energy into the surroundings. It's going to cool down. So this Q1 to 2 indicates there is a process with heat transfer, which is Q, where the system goes from state 1, this initial state where the coffee is at 120 degrees Fahrenheit, to what we're going to call state 2. And of course, state 2 is when if I just set my cup of coffee on the countertop and forget about it, which I very often do, and after a long period of time, this cup of coffee eventually is going to reach what we call thermal equilibrium with the surroundings. In other words, it's going to cool down until eventually it's at the same temperature as the surroundings. So when the cup of coffee has cooled down to 75 degrees Fahrenheit, the same temperature as the surroundings, that's what we call state 2. And of course, the direction of the arrow suggests that the heat transfer is going from the system into the surroundings. In other words, the cup of coffee is cooling down. So after this process from 1 to 2, so this is my state 2, which I've already described to you, after this cup of coffee completely cools, the temperature of the system will now be 75 degrees, which is the same temperature as the surroundings. And now we can ask our question, is this a reversible process? So the question is if this is a reversible process or not, we have to ask ourselves how we would get back to state 1. So think about what we did in the forward direction. We had what we would call a spontaneous heat transfer from the hot cup of coffee at 120 degrees Fahrenheit into the surroundings at 75 degrees Fahrenheit. So we had this heat transfer from the cup of coffee into the surroundings where we had this temperature difference of 120 to 75 degrees Fahrenheit. So how would we get the cup of coffee back to state 1? Well, you already know that we would have to add the equivalent thermal energy of Q1 to 2 back into the cup of coffee. If I want to bring this coffee back up to 75 degrees Fahrenheit, we know from conservation of energy that we have to restore all the thermal energy that was transferred from the cup of coffee into the surroundings. We have to restore that thermal energy back into the cup of coffee to get it back up to 120 degrees Fahrenheit. But how do we get that thermal energy back into the cup of coffee? Well, we know that this Q1 to 2, which spontaneously flowed from the hot coffee into the cooler surroundings, cannot just spontaneously go from the surroundings at 75 degrees Fahrenheit back into the cup of coffee. In other words, I can't draw Q2 to 1 if my surroundings are still at 75 degrees Fahrenheit and expect that Q2 to 1 to heat my coffee back up to 120 degrees Fahrenheit. That's impossible. Because if somehow we were able to do that, if we were able to just start collecting the thermal energy and having it flow back into the cup of coffee, well, eventually my coffee is going to start to warm up. In the moment that my temperature of my coffee goes from 75 degrees Fahrenheit to, say, 76 degrees Fahrenheit, and my surroundings are still at 75, well, now all of a sudden I'm trying to transfer thermal energy from a cold temperature to a hot temperature. And that's impossible. We can't transfer thermal energy from something that's cold to something that's hot. Thermal energy only transfers from something that's hot to something that's cold. So the only way that we can bring the system back to its initial state is to cause a net change to the surroundings. That is, I'd have to make my surroundings hotter than 120 degrees Fahrenheit so that now my thermal energy would naturally flow from the surroundings back into the cup of coffee and then allow my cup of coffee to eventually reach a temperature of 120 degrees Fahrenheit. So I would be changing my surroundings to reverse this process, even though my surroundings didn't change in the forward process. So I would be causing a net change to my surroundings. Because of that fact, because I've created or have made a net change to my surroundings to get my system back to its initial state, I would say that this forward process, as I went from state 1 at 120 degrees Fahrenheit to state 2 at 75 degrees Fahrenheit, this cooling process is an irreversible process. Okay, so that's one example, and we're going to go through now several what I generally call general types of irreversible processes, but we're going to be using examples as we go through the descriptions of these irreversible processes. So in general, if we have an irreversible process where the cooling cup of coffee is an example of an irreversible process, we often will call that irreversible process an irreversibility. So if there's something that causes the process to be irreversible, we call that something an irreversibility. So, what was the irreversibility with this example? As we went from hot cup of coffee to cold cup of coffee because of cooling or heat transfer. So, heat transfer is an irreversibility. And I need to just define or put a little more precision to that and say heat transfer through a finite temperature difference, right? So finite temperature difference means that I can quantify a delta T that's not equal to 0. In other words, 120 degrees minus 75 degrees is a non-zero temperature difference. And so it's what I call a finite temperature difference. So heat transfer through a finite temperature difference is an irreversibility. This cooling process was irreversible as a result of the irreversibility of heat transfer through a finite temperature difference. So I've got more description here in terms of what that means, heat transfer through a finite temperature difference. Okay, and here we, of course, we say that the cooling cup of coffee is an example of this irreversibility. Heat transfer cannot flow from low temperature to high temperature. Therefore, if I have thermal energy flow through a thermal gradient, a temperature difference, from high temperature to low temperature, that cooling process will be irreversible. And likewise, it's, I'm using cooling as an example because of the cooling cup of coffee. The same is also true if I had a heating process. If I heat something from high temperature, if I have something that's cold and I expose it to something that's hot, and I heat that something that was cold, as I bring up its temperature, that too is an irreversible process if that heating occurred through a finite temperature difference. Okay, so why do I have to add this extra statement here on, we say heat transfer through a finite temperature difference? Why can't I just say that heat transfer is the irreversibility? Why do I have to say that it's heat transfer through a finite temperature difference? The reason why is explained in this paragraph here, where we say that, in fact, thermal energy transfer or heat transfer can in fact be idealized as reversible. Okay, there's a very theoretical and idealized situation where if the system and the surroundings are at the same temperature, they could in fact be exchanging thermal energy without increasing or decreasing the temperature of one or the other. In that case, that would be reversible. In other words, the thermal energy could flow just as easily between the system to the surroundings as easily as the thermal energy could flow from the surroundings into the system. So in other words, if I, again, look at my cup of coffee here, where now the coffee is at 75 degrees Fahrenheit, the same temperature as the surroundings, which are at 75 degrees Fahrenheit, my system and surroundings could in fact be exchanging thermal energy with each other, right? In other words, molecules from the surrounding air could be interacting with molecules of the coffee and transferring thermal energy and adding or removing thermal energy between the system and the surroundings. That's entirely theoretically possible. In that situation is the idealized reversible heat transfer. Okay. Now, we're not going to talk about that idea again for a little bit later on, but that will be an important construction for us when we talk about basically what we call heat engines and heat pumps later on this semester. Okay, but I won't spend any more time talking about it right now. Okay, what's another example of an irreversibility? Well, probably the easiest one to think about, and perhaps the most famous, is of course friction. Okay, so you know that anytime you have friction, you basically are transferring work, or you're having to expend additional energy to overcome that friction. But that additional energy that you expend to overcome friction, you'll never be able to get that back from friction, right? In other words, if I take my hand and I set it on top of the table surface, and suppose I start sliding my hand to the left, well, my muscles in my arm are transferring energy to slide my hand across the surface of the table. And so there's a certain amount of work that my muscles are putting into my hand to cause that displacement. Well, that's the work energy, right? I have a force applied by my muscles to move my hand, a displacement. Work is force times displacement. But in addition to that energy I have to provide to displace my hand, I'm also applying work to overcome friction. And that additional energy that I apply to overcome friction, I can't get back. So in other words, if I were to then reverse the direction of my hand and go back to the right, from a physics definition, my force is now in the opposite direction, and so my work is now being recovered, if you will. But the work or the energy that I put into overcoming the friction is still being expended by my muscles. In other words, I can't recover that energy that I'm transferring to overcome friction. Therefore, friction is an irreversibility, okay? And there are lots of examples of friction, right? Sliding a box along the floor, rotating shafts and bearings, piston rings against a cylinder. There's fluid friction with, bodies that are moving through air, such as aerodynamic drag or hydrodynamic drag if a ship is sailing through water. All of these interactions are friction interactions, and of course, energy must be expended to overcome that energy. And the statement that's written here, we cannot get that energy that's expended to friction back as useful work. The energy is still there, right? So again, if I use my hand sliding across the table as an example, if I do that rigorously and fast enough, eventually I start to feel my hand warm up. Well, what I'm doing is the energy that I'm expending to overcome the friction, what the friction is doing is it's taking that energy, it has to do something with it. So it's taking that energy and it's basically dissipating it or disordering it, if you will, into thermal energy. And I start to feel that as, my hand starts to get a little warm as I slide it back and forth across the table. So energy is conserved. I'm doing something with that, or that energy is going somewhere. But the problem is that once that energy dissipates as thermal energy, I can no longer recover it as useful work. So I put work in the forward direction, but I don't get work out in the reverse direction. Therefore, friction is an irreversible process. Another type of, another general type of irreversibility is what I call mixing, okay, or what we call mixing. So in the case of mixing, we have here this example where there's a sealed box and there's a divider that separates this sealed box. And on one side of the divider, I have, say, for example, nitrogen gas. And then on the other side of the divider, I have oxygen gas. And because of this divider here, these two gases are not interacting with each other. They're not in communication, if you will, with each other because this divider is here. So I call this state 1, and I have this nice idea, or I have information about my nitrogen gas. In other words, I know all of my nitrogen gases on this side of the box. And I know all of my nitrogen gases on this side of the box. So I have a certain amount of certainty as to where stuff is. So if I were to just randomly put my mouse here, and I were to say, what is this hand touching? I can tell you with a certain amount of certainty that that hand is touching nitrogen gas. Or if I were to just randomly, and then my hand drops here, and I say, okay, what molecule is my hand touching? I can say, well, it's touching oxygen gas because of this separation with this divider. Now, let's remove the divider, and that'll be process 1 to 2. Process 1 to 2 removes this divider. And of course, we know that because these two species are different, and because now when I remove this divider, this nitrogen gas no longer sees a volume that ends here. It now sees a volume that ends way over here. And likewise, this oxygen gas no longer sees a volume or a space that ends here. It now sees a space that ends way over here. So the nitrogen has a tendency to move in this direction, and the oxygen has a tendency to move in this direction. And as a result of that, the nitrogen and the oxygen gases are going to mix. So that after a period of time, when things are completely stabilized and we reach a condition of what is called equilibrium, that is, the system is no longer changing, now I have no longer all my nitrogen on one side and all my oxygen on one side, but I now have a mixture of nitrogen and oxygen all mixed together at state 2. Okay? Now, if I wanted to go back to my initial state, can I just wait long enough for these two gases to separate naturally? That's all I had to do for the mixing. All I had to do for the mixing is just remove this divider and just wait, and the two gases mix. But now I want the gases separated. I don't want them mixed. So I'll just keep on waiting, and since they naturally mix together, then maybe it makes sense that they'll just naturally separate. Will that happen? Of course it won't happen, right? That's impossible. And so the only way we can separate these two gases is by having the system interact with the surroundings, right? We would have to do some kind of gas separation process to get all the nitrogen back on this side and all the oxygen back on this side so that I can then insert my divider and have them be separate again. Okay? In the forward direction, I didn't have to do anything. There were no gas mixing processes. I didn't have any work transfer. I didn't have any heat transfer. But in the reverse direction, I'd have to have those interactions to get these two gases separated. So mixing is an irreversible process. Okay? And now if I also, we were talking before about, if I put my hand here, I know I'm touching nitrogen gas, and if I put my hand here, I know I'm touching oxygen gas. But now what if I put my hand here? Can you tell me with 100% certainty that my hand is touching nitrogen? Or that my hand is touching oxygen? No, you can't. Not with 100% certainty. There's a probability that I'm touching either nitrogen or oxygen. There's very low probability that I'm touching argon or helium. But if you wanted me to tell you if I'm touching nitrogen or oxygen, well, I can't tell you that with 100% certainty. In fact, if in my initial state, if the number of particles of each of these gases were exactly the same, so that after they mixed, 50% of my mixture is nitrogen and 50% is oxygen, then there's a 50% chance, in fact, that my hand is touching, say, nitrogen. And there's a 50% chance that my hand is touching oxygen. But before, I could tell you 100% what my hand was touching. I could tell you with absolute certainty what my hand was touching. So we've actually lost information. We've lost certainty that I can tell you exactly how my system is behaving. And remember that entropy is the quantification of the improbability to describe the behavior of a system. In other words, I've lost information as I underwent this irreversibility. I've generated entropy. I've generated improbability that I can describe my system. That's what entropy generation is. It's the loss of information as I undergo an irreversible process. Okay, so to summarize, in the forward direction, where I'm mixing the two gases, there is no interaction with the surroundings. As the gases mix, I didn't have to do anything at all. But if I wanted to unmix the gases, then I would have to have some kind of interaction with the surroundings to separate those gases. Okay, so another type of irreversibility is electrical resistance, right? And so, of course, we know that when an electric current flows through a conductor, it meets resistance. And really, electrical resistance is nothing more than a type of electrical friction, right? So like friction, this electrical resistance expends work energy. It basically decreases the quality of that electrical current, and that electrical resistance, or that energy that's expended to overcome that electrical resistance, cannot be recovered. And so electrical resistance is an irreversibility. Okay, another example is what we call unrestrained expansion. And sometimes this one is easy to visualize. So I've drawn this picture here. And so in the case of, so don't let the word unrestrained expansion scare you. I mean, one of the problems with this irreversibility is that we give it this crazy name, and it's, very, I mean, first of all, not all of us are familiar with what expansion necessarily means. And then you throw this word unrestrained in front of it, and it's like, oh, good grief, I have no idea what this means. But it's actually much simpler than it sounds. Okay, so focus on this picture that we have here. And what this is a picture of is it's a container, and it has a valve at the top, right? So this is basically a valve, and this valve can open and close. Right now it's in its closed position so that this container is sealed, okay? So the container is holding a gas, and the gas is at a higher pressure than the surroundings, right? So that's what I write here. Pressure of the gas is greater than pressure of the surroundings. And of course, we know exactly what's going to happen if we open this valve. If we open this valve, the gas, so this is process 1 to 2, if we open this valve, the gas is going to flow out, right? The pressure of the gas is greater than the pressure of the surroundings. And when the valve is closed, that is blocking or separating the gradient, the pressure gradient that exists between my system and the surroundings. But if I open that valve, I allow my surroundings to mechanically communicate with my surroundings. I allow my system to mechanically communicate with my surroundings. And so that pressure gradient will then drive my gas to flow out of the system. And that's what I draw over here. The pressure of the gas is greater than the pressure of the surroundings. And so that's going to drive my system, the mass of my system, to flow out into my surroundings. And that process will continue until either I close my valve, but let's suppose my valve stays open, in which case that process will continue until the gas pressure attains equilibrium, what we call mechanical equilibrium, with the surroundings. So in other words, the pressure of my gas in my system eventually will match or go to the pressure of my surroundings as the mass leaves the control system. Now, of course, once the pressure, so all I did to cause this process to move forward, all I did was open the valve. And then I didn't have to do anything else. I just opened the valve and let her rip, okay? So once the pressure of the gas equals the pressure of the surroundings, the gas that's left in the container is not going to spontaneously, or excuse me, the gas that left the container, right? So this gas that flowed out into the surroundings, it's not going to just spontaneously flow back into the system and do so until the pressure of the gas returns to its initial state where it was greater than the surroundings. That's impossible, right? It's not going to spontaneously do that because, again, it's just like this idea that we had with the cooling cup of coffee. The minute that particles start to flow into my system and the pressure of my system starts to get a little bit greater than the pressure of my surroundings, well, now I have an inverse pressure relationship, and my particles are just going to naturally flow back into the surroundings just like they did in the forward process. So it's impossible for all the gas particles that flowed out of my system to spontaneously flow back into my system. The only way I can return my system back to its initial state is by having there be an interaction with the surroundings that was not present in the forward direction. In other words, I need to transfer energy to pump or push my gas back into the system and return the system to its initial state or its initial pressure where that pressure was greater than the surroundings. That energy transfer wasn't present in the forward direction, but it would be required in the reverse direction to get the system back to its initial state. Therefore, that forward process, that unrestrained expansion, right? In other words, there's nothing restraining the flow of this gas to the surroundings. So when we say expansion, that means that we're going from high pressure to low pressure. So in this expansion of the high gas, the high system pressure, dropping to the surroundings pressure, that's the expansion part, it does so unrestrained. In other words, there's nothing that's restraining this flow of the system gas into the surroundings. It's just flowing naturally, okay? And so that is an irreversible process, what we call an irreversibility. Now, we can expand a gas reversibly, and we'll talk about that later on in this video lecture. Another type of an irreversible process, or another type of irreversibility, is of course a chemical reaction. And so several chemical reactions are irreversible. Not all of them are, but most of them are. And one good example, of course, is when concrete cures, right? So I know the civil engineers listening to this know this, but mechanical engineers or industrial engineers or petroleum engineers, you may not know that curing concrete is a chemical reaction. And in that chemical reaction, it's actually an exothermic chemical reaction. And so that curing concrete has a release of thermal energy during that chemical reaction. The concrete actually gets hot. In fact, sometimes concrete can get so hot during the curing process that you have to actively cool that reaction because you can weaken your concrete, you can weaken your cure if that thermal energy is not properly removed during the curing process. So, in the forward direction of this chemical reaction, in the curing of the concrete, you go from water and limestone, mix them together, and a reaction begins, and concrete starts to cure, and thermal energy is transferred from the system, you're curing concrete, into the surroundings. But if I do that reverse, if I take that thermal energy that was added to the surroundings and I transfer it back into the cured concrete, I'm not going to undo the concrete and get limestone and water. I'm just going to raise the temperature of my concrete. So chemical reactions are generally irreversible processes. Another good example of an irreversible chemical reaction is combustion, right? I have, say, a fuel, and I react it with oxygen, and I get products of combustion, like, say, carbon dioxide, if it's a hydrocarbon fuel, and water, if it's a hydrocarbon fuel, and a few other species. And, of course, I release thermal energy in that chemical reaction. But if I take carbon dioxide and water, and I add thermal energy to it, an equivalent amount of thermal energy, I'm just going to get hot CO2 and hot water. I'm not going to get fuel and oxygen. So again, chemical reactions are generally irreversible processes, irreversibilities. Okay, so lots of discussion here, right? Talking about different irreversible processes, and a very legitimate question now is, well, why is all of this important? Why is it important to know the difference between a reversible and an irreversible process? Well, it's important because irreversible processes generate entropy. When we were talking about mixing, the mixing example up here, I talked very briefly about how we went from a condition of relatively low entropy, where I had high certainty, I had high probability that I could define the behavior of my system, to a condition of high entropy, where I lost information. I lost probability that I could tell you the behavior of my system. So I went from low entropy to high entropy. And I didn't do anything else to add entropy to this system, right? If I think about my second law equation, I could add entropy to this system by transferring mass into it. Well, it's a closed system, so I'm not transferring mass. Or I could add entropy to this system by adding thermal energy with heat transfer, right? Recall your second law equation. But I didn't do either of those things in this process, right? I didn't add thermal energy, and I didn't add mass to my system as I went from this state to this state, but my entropy increased. I have less certainty, you know, I can't tell you with the same certainty what my hand is touching when it's right here, as opposed to the certainty that I had when my hand was right here. So I've increased the improbability that I can tell you what's going on inside my system. I increased entropy. So how did I do it? Well, I did it by generating entropy. And that entropy was generated because this system underwent an irreversible process. So whenever we say that a system undergoes an irreversible process, what that directly means in the context of the second law is that it generated entropy. Irreversible processes generate entropy. So let's just remind ourselves where this entropy generation appears in our second law equation, right? So this is our general equation. And of course, our general equation says that the change in entropy of a control system is equal to the entropy that flows in with mass flow rate minus the entropy that flows out with mass flow rate, plus entropy that's added or removed through heat transfer, plus entropy that's added with generation. So this S dot gen term that's in our second law equation is the result of irreversibility. We also have our steady state open system equation. So remember, this equation here is nothing more than this equation with our ds by dt term equal to 0 because we're saying it's steady state. And so again, that S dot gen term appears in our steady state open system equation. And again, that S dot gen term will always be positive if our process is reversible. And then of course we have our transient closed system equation, where now, of course, it's, again, starting with the general equation. It's a closed system, so our m dot terms canceled out. And because it's a transient process from a given initial state to a given final state, 1 to 2, we can integrate with respect to time, and we get this form where the change in entropy of our system is equal to the entropy that's added or removed with heat transfer, plus the entropy that is added with entropy generation. And again, this entropy generation term is present when there is an irreversible process. So in each of our second law equations that we're going to use this semester, an entropy generation term exists. And since entropy represents the unavailable portion of energy for conversion to useful work, entropy generation represents the degrading or the destruction of useful work. Okay? So I've underlined this because this is one of the critical things we want you to learn this semester. Entropy represents that portion of energy that I cannot convert to useful work. Just like friction. If I transfer energy into a system that has friction, that friction takes a portion of my energy. And I had to put work in to overcome that friction. I can't get that energy that I put into friction back as work energy. That's impossible. That friction generated entropy. That friction represents the degrading or the destruction of useful work. Once I transfer that work energy into friction, I've destroyed that energy's ability to do useful work. I haven't destroyed the energy. I'm not suggesting that I'm destroying energy. What I have destroyed is the energy's ability to do useful work. Okay? I've degraded the quality of that energy. Remember that quality indicates the ability or the capability of energy to do useful work. So, knowing that, we can now say what the fundamental statement of the second law says. And the fundamental statement of the second law of thermodynamics states the following. The net or total entropy of a system surroundings interaction will always increase, or in the best case scenario, stay the same. Net entropy of a system surroundings interaction can never decrease. And you might now start to get the sense that based on our examples of irreversibilities, the net entropy, or that is the difference in the change in entropy of a system and surroundings will always be positive for irreversible processes. If I have to change my surroundings, if I have to do a net permanent change to my surroundings to get my system back to its initial state, then I have increased the net entropy of that system surroundings interaction. And the second law says that net change of entropy will always be positive, or in the ideal sense, the theoretically ideal case, stay the same. What is impossible is for that net entropy of a system surroundings interaction to be negative. That can never happen. Okay, that would be the case of impossible process. Okay, so if I bring this back to entropy generation, what this means in terms of entropy generation, the fundamental statement says that entropy generation can never be negative. Entropy generation can be positive, in which case we have an irreversible process, and in the situation of entropy generation being positive or greater than 0, that means that we've destroyed the usefulness of energy. In other words, that element or that fraction of energy that was available to us for conversion to useful work has been destroyed. It's no longer available to us. The energy is not destroyed, just its usefulness. So if I expend energy to overcome friction, that's it. I'm done. I can't get that energy back as useful work. I can't pull that energy back out of friction and use it to spin a shaft or use it to push a piston. That availability of energy to do useful work has been destroyed. I can also have entropy generation equal 0. This is the ideal case. This is the situation where we have a reversible process. So if I have a reversible process, my entropy generation is equal to 0. And what this means in the context of the usefulness of energy is that my usefulness of energy for conversion to work, to useful work, is maintained or conserved. I haven't created it. I haven't created utility or usefulness of the energy, but I also haven't destroyed it. It has stayed the same. That's the situation of a reversible process. What's impossible, what the second law of thermodynamics says is impossible, is if entropy generation is less than 0. The second law of thermodynamics says that entropy generation can never be less than 0. This is impossible. And what that would imply, if we ever had a situation where entropy generation were less than 0, that would imply that the usefulness of energy somehow spontaneously increased. And that's impossible. So, what would it mean? Like, what's an example of entropy generation being less than 0? Like, how could I imagine a situation where I'm somehow spontaneously increasing the usefulness of energy? Okay, well, and we could use any one of the examples any one of the irreversibilities that we described, but I thought maybe perhaps the best description would be looking at our container, our sealed container with a valve at the top. Okay, so suppose we have our container of air, right? So this is now our container of air. It looks a little different than I drew it above, and I'll describe why in just a minute. Okay. So we have our container of air, or I guess I used gas earlier, so this is our container of gas. And we still have a valve at the top, right? And right now the valve is sealed. But this time, rather than having a rigid bottom, or a rigid seal on the bottom, now I'm going to replace that rigid bottom with a movable piston. And so this movable piston can move up and down. It still seals, right? Even though I drew a gap here, this is where we usually have piston rings that seal the system from the surroundings. So this piston is still sealing the bottom of the container, but now it's movable. It can move up and down, okay? So in this drawing that I have here, where I have my system, so my system is the gas that's trapped between the piston and the rigid walls of the container and the valve, okay, which the valve right now is closed. And I'm saying here that the pressure of the system, my gas, is greater than the atmospheric pressure. So this system here is interacting with this surroundings where the surroundings are at atmospheric pressure. Okay, so this is, say, state 1, where the system pressure is greater than the atmospheric pressure. Since the system pressure is greater than the atmospheric pressure, and because this piston can move, the piston or the pressure forces of this system will push down on this piston, which will cause the piston to move down. And because these pressure forces are acting through a displacement, and since we know that work transfer is a force acting through a displacement, as this piston moves down, I'm transferring work from the system into the surroundings. That's what I've drawn here with, when the piston is moving down, I'm transferring work out of the system. Now, if I wanted to, I could very easily reverse this process, right? And so if I sort of imagine an ideal situation where there is no friction between the piston and the walls of the container, let's just, for sake of idealization, let's suppose that there's no friction, in these seals here between the piston and the walls of the container. Okay, so we have this ideal case, and in the ideal case where there is no friction between the piston and the walls of the container, we can say that that work transfer is reversible. Why is it reversible? Because in the forward direction, I transfer work from the system to the surroundings. That's what I call work 1 to 2. And that work transfer could continue until, let's say, the system pressure equals the atmospheric pressure, until we have mechanical equilibrium between the system and the surroundings. But because I transferred that work out and there was no irreversibility like friction, well, I can just as easily now take that work energy which was transferred out, this work 1 to 2, right, as my piston went from this top position at what I call state 1 to this bottom position, which I'm using the dashed line here as the outline of the piston, to state 2, I can take that work transfer and I can reverse it. And I can now put that work transfer back into the system. In other words, I can transfer that work from the surroundings into the system, where now I have work 2 to 1, which is the negative of work 1 to 2, and I can push that piston back up to its initial state, where because I'm now compressing my gas, the pressure of my gas will return to its initial pressure, which was greater than the atmospheric pressure. This is how a piston cylinder arrangement works, and this in fact is what we have in our automobile car engines, for example. We have pistons that basically go up and down all day long, transferring work out and allowing our cars to move forward. But because I was able to restore both my system and surroundings to their initial state after the forward and reverse processes, I can call this a reversible process. And because it's reversible, I can say that I've generated no entropy. So my entropy generation is equal to 0. Well, let's suppose instead that it were a real case. And because this is, the reversible case is an idealization, okay? But let's suppose this were a real case. Well, if it were real, then we know that one irreversibility that's going to exist for sure is friction. So if instead this were a real case where friction is present, well, then the real work, the actual work that I get out of my forward process as I go from state 1 to state 2, this work that I'm actually able to transfer out of my piston is going to be less than the work that I would have transferred out if it were a reversible process. Why? Because I have to use a portion of the energy of this system to overcome friction. So my reversible ideal work is the summation of my real work, the work that I actually get out, plus the work that I had to expend to overcome friction. Well, this work I can get back, right? I've transferred this out to the surroundings, and because it's mechanical energy, it's high quality energy, I can get this back and I can pump this back into my system. But this I cannot get back. I can't get this friction work back out But if I want to return my system back to its initial state, this is the amount of work I have to put into the system. So I transfer this much energy out of my system. I only get this much actual work from that process, and this energy that I had to expend to overcome friction is gone, and I can't get it back. I can't recover it. So it's what I call lost or destroyed opportunity to do work. It's an irreversibility. It generates entropy. So Sgen is greater than 0. Okay, well now let's think about this fun, crazy case. Let's suppose that we have this situation here where now at state 1, right? So I go back to my state 1 where my the pressure of my system is greater than the atmospheric pressure, right? And I have my valve up here and my piston is up top at the state 1 position. And now let's suppose that before my system gets a chance to push this piston down, my valve opens. And because my valve opens, just like we described above when we talked about unrestrained expansion, because this valve has opened, and because my system pressure is greater than my atmospheric pressure, I know what's going to happen. My gas is going to flow from my system out into the atmosphere. And that process will continue if my valve stays open long enough. That process will continue until my system pressure equals my atmospheric pressure. And all the molecules that had been inside my system that flowed out are now scattered in the atmosphere, all at atmospheric pressure. Okay, well, geez, that was a mistake. I didn't want to do that. I wanted to transfer work out of this system. So now, how do I get it back to my initial state? Right? So after all the gas leaves the container through the valve, I want to get that gas to flow from the surroundings back into the container. I want to restore this opportunity to do useful work. I want to get back to my initial state. So all I'm going to do is I'm just going to wait long enough for all those gas molecules that left my system. They're still out here in the atmosphere. And I'm just going to wait long enough until they corral themselves and just start to pile themselves back into this system. And after a period of time, after these particles just naturally flow back into my system, because those particles are back inside my system pressure will go back to its initial state, and my system pressure will be greater than the atmospheric pressure. And I'll just close this valve and keep those particles in there. And now, because I have this pressure gradient, I've restored my opportunity to do useful work. Up here, I had lost my opportunity to do useful work, right? But I've just waited long enough, and I've restored that opportunity. Is it possible? Well, of course it's not possible, right? I mean, this is an incredibly crazy idea, right? And it's crazy because it's impossible, right? This is not possible. It's a silly idea. And what that would mean is I've naturally, spontaneously added quality to energy. I have spontaneously created an opportunity to do useful work. Well, in the forward direction, I destroyed the opportunity to do useful work. I opened the valve, and I vented all the gas, and I eliminated that pressure gradient. I destroyed the opportunity to do useful work. I generated entropy. That's what entropy generation is. To go in the reverse direction, for all those gas molecules to spontaneously corral themselves and restore that opportunity to do useful work would mean negative entropy generation. It would mean Sgen less than 0. But that's an impossible idea. That can't happen. And that is what the second law of thermodynamics says. The idea of spontaneously adding quality to energy, the idea of spontaneously making energy more useful than it really is impossible. That's a violation of the second law of thermodynamics. That is a situation where Sgen is less than 0. And so what we really need to know about the second law of thermodynamics this semester, what I really want you to understand, is that what the second law of thermodynamics says is that it is impossible to spontaneously increase the quality of energy, which is to say that it is impossible to spontaneously increase the usefulness of energy to do work, which, as we described in lecture, that quantification of the usefulness of energy to do work is called exergy. And so to spontaneously increase the exergy of a system is impossible. It's certainly possible to spontaneously destroy the exergy of a system. That's what we did up here. Up here, when we had our system with pressure, that system had exergy. It had a capability to do useful work. But we opened the valve and we vented the gas into the atmosphere. And we no longer have that capability to do useful work because now the system is at the same pressure as the atmosphere. So we destroyed the exergy of the system. We destroyed the capability to do useful work. To go back to create exergy is impossible. That's a violation of the second law. Okay, ladies and gentlemen, this concludes the enhancement lecture on irreversible, reversible, and impossible processes. Again, we're going to continue to talk about this all semester long, and so feel free to refer back to this lecture as often as you need to. And if you have any questions, of course, you are welcome to stop by and visit with me. Thanks very much and have a good day.